Hi, can you hear me? Because
Yes.
somehow my internet connection is a bit unstable, so I'm a bit nervous. Can you hear me now?
Yes,
Geraldine.
yes, I can. Yeah.
Okay. Very good. So let me share my screen. So first of all, thank you very much to the organizers for setting up this meeting and for the invitation. So during this talk, before I move to the main topic given by the title of the talk, I would like to make a few comments to stress motivations for ultra-high frequency gravitational wave detectors, following up on the previous talk and really illustrating this on primordial sources of gravitational waves. And all this talk, relies very heavily on the work done by my young collaborators, Pira Simakashon and Yann Goudenoir. And in fact, every single plot in this talk was made by Pira. So let me start with discussing the main three sources of primordial gravitational waves. We discussed inflation, first order phase transitions, and cosmic strings. These are the three main canonical, very much studied gravitational wave signals. We have this primordial inflationary signal, which is essentially flat here. And I will discuss this. I want to explain really the role of non-standard cosmology, how this can affect the spectrum, because this flat prediction is really following for the assumption of radiation. So first, I would like to, a very important aspect is really the relation between the frequencies that we observe today and the typical physics energy scale at which gravitational waves were emitted. So there is a very simple relation in the case of short-lasting sources. So if you define T star, the temperature of the universe at the time of emission, and F star, the frequency at the time of emission, the frequency you observe here is given by this formula. So essentially, you relate the frequency F star to the Hubble scale at the time of emission. And so, as you know, for temperature around the electroweak scale, the frequency is in the millihertz, and you get a signal in the Lisa band. So essentially, Lisa is a window on the TeV scale, Einstein telescope and Cosmic Explorer would be window on the PeV scale, and pulsar timing arrays are somehow sensitive to energy scales around QCD. So we want to discuss now very high frequency gravitational wave detectors, which means typically the energy scales that we are probing are really beyond the PeV. So that's very exciting because these are energy scales we cannot probe at colliders. So let me, I just would like to show a few natural signals beyond the kilohertz. Since the gravitational waves from first order phase transition have been really studied a lot recently, this is a very simple plot. You can just translate the usual signal you find in the LISA range from TeV scale physics. And you see here that first order phase transitions happening at temperature, say 10 to the 9 GeV, will not be visible at all by any of the planned experiments, and they would instead show up at these very high frequencies. So that's one motivation. You could say if you have an experiment sensitive in this frequency range here, you will be able to probe this type of signal, which is for typical, parameters characterizing the phase transition here. This is the latent heat, the amount of latent heat, and the amount of supercooling. Okay, so that's one example, which I think is quite a strong motivation already. And now let me move to long-lasting sources. So these phase transitions are really mainly short-lasting. And now I want to discuss in the rest of the talk long-lasting sources, meaning that you have emission for really many Hubble times. And in this case, there is a much less trivial relation between the frequency today and the typical physics energy scales that you can describe. So a very famous example is cosmic strings, so gravitational waves from loops, from cosmic loops. So here there is a summary. In blue you have the total spectrum, and you see the different, the contributions from emission in matter era and emission in radiation era. And what I wanted to stress here is this high frequency cutoff, okay, which you would not be able to see at all in all these planned experiments. But in high frequency gravitational wave detectors, you would, you see, in principle, have a signal here, an interesting signal, which would tell you something about very high energy phenomena. And in fact, we had this discussion on Tuesday after the talk by David Dunsky, because in fact, he was not showing this cutoff here. And interestingly, so you first have the cutoff from the formation of the network, right? But you may have some cutoff at lower frequencies, particle production instead of gravitational wave emission. And depending on the structure of your loops here, whether you have this small scale structure as kings or cups, you have different types of cutoff. There is also possible cutoff coming from friction due to interactions between the strings and the plasma. So this is some interesting physics, which in principle you would, you know, if you had access to this frequency range, you would learn something here about this phenomenon. So in fact, one can derive precisely the frequencies for these different cutoffs. So I'm just flashing this now, tell you that these relations exist. So there is a clear formula here for the formation cutoff, for the particle production cutoff. You have this cusp of kings, the thermal friction effects. And what I would rather discuss today is really the effect from non-standard cosmology. So usually in the literature, one assumes radiation, a long radiation era after inflation. But if you have some matter era inside the radiation era, or you had some late, very short inflation eras, this can have a dramatic effect on your spectrum. And you could read, if you were able to measure the spectra, you would be able to access the energy scale at which this modified equation of state for the universe would happen. So this can be summarized here. So this is again a spectrum coming from local cosmic strings for different string tensions. And okay, so here this is a prediction from standard cosmology. And I'm showing what I was just discussing before, the position of the different cutoffs due to different effects. You can see them here. Okay, so this is for standard cosmology. And in addition to this type of high frequency cutoff, you could have some turning point frequency due to non-standard cosmology. So the impact of the cosmological history and gravitational waves has been studied. There was this paper by Marek Lewicki and collaborators in 1718. And then we studied this also with Jan Gutenoir and Pirasima Kashon for cosmic strings, and there were a number of other papers. So for sure, you will have a very strong impact here on the gravitational wave spectrum from either you see this long matter era or some kination era happening after inflation. So one of the most striking effects would be this kination era. So what is kination? Kination is a period where the energy density of the universe is dominated by the kinetic energy of a scalar field. And I will motivate this very soon. In this case, you have an enhancement of the signal. And here is an example. Okay. But this leads to actually two very large spectrum, which is actually excluded by Big Bang nucleosynthesis. And now there is another possibility, which is instead a suppression coming from a late inflation era. So here you see how the cosmic string spectrum, so here in black, you have the standard spectrum, standard cosmology. And let's say you have a very short era of inflation, and this would lead to this suppressed spectrum here. And so this depends on the duration. NE is the number of P4, so the duration of your inflation era. And the position of this turning point will depend when this is taking place, when this inflation era is taking place. So there are many interesting types of spectra you can get. And by measuring precisely such a spectrum, you could read really the cosmological history. So this is, again, different types of spectra from cosmic strings, from local cosmic strings. And now I'm showing the position of the positions of the turning point frequency, but now due to non-standard cosmology. So if you had, let's say, an era of either a matter era or a kination era taking place, let's say at 10 TeV, this would show up in the Einstein telescope bound. On the other hand, LISA would be actually sensitive more to the QCD scale. So you see it's a bit counterintuitive because now LISA, for the case of long-lasting sources such as cosmic strings, the turning frequency here, actually, you don't see the relation between TeV and LISA. Now what you see is actually that LISA is sensitive rather to QCD scale when you have a non-standard cosmology at that scale. So it's a less trivial relationship between measured frequency and typical energy scale. Okay, so one can see different frequencies here, and I wanted to stress this because obviously now if you go to high frequencies, you can probe higher and higher energies. Okay, and so now last interesting type of spectrum you could get, again from cosmic string networks. If you now have metastable cosmic string networks, you have a low frequency cutoff. And you see you could get this funny spectrum here with a peak structure, which would not show up in any of the planned experiments. So for instance, if you take here, this one, you would have a peak really at very high frequencies. And this looks like a peak, but this comes from cosmic string networks. So that's quite interesting. It's not the usual cosmic string spectrum you are used to, right? So just summary of these parts. High frequency gravitational wave detectors, there would be a unique window on very high energy and fundamental physics, particle physics. You can probe high temperature phase transitions, the early properties of cosmic string networks, interactions of these networks, their decay, and what I'm stressing mostly in this talk is really the non-standard cosmological histories like early matter era, short, late inflationary stages, or short kination era, as we will see now. So let me now move to the main topic of this talk. And I want to make the connection between this kination era I've been talking about and axion physics. So there is this very interesting enhancement of any primordial signal, long-lasting primordial signal from kination. And now I want to motivate such kination with axion physics. So again, let me show this again. This is a standard cosmological evolution, inflation, standard radiation. And what would be the irreducible gravitational wave background from quantum fluctuations during inflation, as we just discussed, it's very small. And here this is for an inflationary scale of 10 to the 16 GeV. And the flatness comes from this radiation era. Now, if I modify this cosmology, and for instance, I modify it in blue like this, I have some stage of matter era inside the radiation era and followed by a short kination era. And this cosmological history would lead to really this very interesting peaks structure. So this is really gravitational waves from primordial inflation. And this gets enhanced by this non-standard cosmology. So you get this peak here. So in fact, this was known and they have been studied about constraints from so in particular, Daniel studied this a couple of years ago, that a very long kination era after, so not during radiation era, after inflation, this would lead to too much radiation from gravitational waves and you have a strong bound from BBN. So in fact, it turns out that BBN constrains very much this long kination era after, right after inflation. And what I want to stress now is that instead, if you have a short and low scale kination era, this is something that you can probe at future planned gravitational wave observatories. And there are also very interesting signatures and quite well motivated signatures at ultra high frequencies. So before I move to this short kination era inside radiation era, I wanted to show this. These are the constraints on a long kination era following inflation. And this is what I was just telling you, that actually BBN excludes any prospects of observation by LIGO, LISA, ET, and BBO. So because of this BBN bound, there is no way you can expect to see enhancement at planned observatories. On the other hand, at ultra high frequencies, there is still a window. So if you had ultra high frequency experiments with such sensitivity, you would actually still be able to constrain a long kination era. So this plot is in the plane reheating temperature, inflation scale. Okay, so we can come back to this if there are questions later. But the main message here is that none of the planned experiments can observe kination-induced gravitational wave enhancement from a long kination era after inflation, except, so now high frequency experiments would have, there would be a potential. Okay, so now I move to a very short kination era. And so what triggers the kination era? Answer is a spinning axion. So what is a spinning axion? So in most of the literature on axion cosmology, one assumes that the axion is at rest, and eventually when its mass becomes of the same order as the Hubble scale, it starts oscillating, starting from an initial vanishing velocity. However, there are good reasons to expect that in some number of models, this is not what happens, and you actually have an initial velocity for the axion. And this leads to very interesting physics. So now I'm giving up the assumption of vanishing velocity. And they were, in fact, in the last couple of years, a number of papers, mainly by Harigaya et al., this idea of kinetic misalignment, so revisiting the abundance of dark matter when taking into account the velocity of the axion. Okay, so there are two main types of models which can lead to this natural velocity. So first, you can consider the full complex scalar field. So you have your U1 symmetry, which is spontaneously broken by the wave of a new field phi. The axion is the angular mode, and usually you forget about the radial mode. You say it's frozen, you don't have to worry about it. But in fact, the dynamics of the radial mode can give a kick to the axion and induce a large initial velocity. So here I'm showing the potential and what could happen if you start at large initial vacuum mix value for your Pechequin field. And you would end up here with this blue orbit with an axion which is spinning around. At this stage, the mass of the axion is still 0, and later on it will develop a mass. But before it develops a mass and start oscillating, you have this stage of spinning, which will trigger a stage of kination. There is a very other interesting framework where you don't have to think at all about the radial mode and just think about your axion only. And in this case, you could give it a velocity by assuming that at very high energies, the axion potential actually is very different from today. So you have a very large mass at early times. Then at some temperature T, this potential vanishes, and this gives a kick. So the dynamics is such that you give a kick when the potential, when you have this phase transition, you give a velocity to your axion, and later on the low energy mass of the axion will develop. But in the meantime, you will have a period when the axion is spinning. Okay, so these are for the motivations. Okay, so hopefully you are now convinced that a kination era can happen naturally. And now let's see the consequences for gravitational wave signals of primordial origin. So I'm now going to have this so I have my usual standard radiation era, and at some point, my energy of my scalar field will dominate. I first have a matter era, and eventually kination era. So kination era means energy density redshift like a to the -6. Okay, and so here at this point, you define this typical energy scale of kination, which is given by the velocity of the axion and Fa, the Pechequin scale, if you want. Okay, so a very important quantity is the duration of kination, NKD. And so one can show the results in a completely model independent way just as a function of EKD, energy scale of kination, and the duration of kination and KT. So this is just a simple sketch to show how one enhances the gravitational wave signal because of this non-standard cosmological evolution. One can derive the formula for the peak frequency and for the amplitude at the peak. So these are the very important plots. Let me show you. So these are the typical spectra that you would get. So once again, this is just gravitational waves from inflation, the irreducible background. So it's kind of very generic. I'm not assuming anything about inflation, except that it happened at some energy scale 10 to the 16 GeV. And because of this non-standard cosmological evolution, I have triggered this peak here. Okay. So now, of course, the key question is about the position of the peak, and the position of the peak is controlled by the energy scale of kination and the duration of kination. You see, you have this exponential dependence on the number of E-folds of kination. Okay, so these are for, you see, these spectra are for different, you can see the benchmark points here, they correspond to different kination era and kination duration. I don't need a very long kination era. I mean, a few E-folds are enough to lead to these observable signals. So let's take this black dot because this is a very exciting QCD case which falls into a very high frequency range. So what until now, these curves are kind of very model independent. They only depend on energy scale of kination, duration of kination. Now let's connect these two Axion models. And these straight lines here show the lines where I will have the correct relic abundance of dark matter for the QCD axion. Okay, so as you see, I have different lines. I have different QCD axion models. So the conventional one, the one that we are all familiar with, is this here. And so there is a very clear prediction here that for the QCD axion, you will be outside of the range of planned experiments. And this is something you could only see with ultra high frequency detectors. I'm showing lines now where there are these modified models where you modify the relation between MA, the axion mass, and FA. And this was in particular worked out by a paper by Andreas, who is here in this workshop, and collaborators. This leads to very interesting phenomenology, and I'm showing what kind of signals you would get for these models. Okay, so on the right, you just see the observable prospects for different experiments where you could in fact probe a kination era. So that's quite exciting. And now let me stress again the case of the QCD axion, just to explain how we can relate this gravitational wave signal to the relic abundance of the QCD axion. So in fact, the Pechequin charge in the spinning axion transfers to the axion number density. So there is a relation between the velocity of the axion, the relic abundance today of dark matter, and you can in fact derive a relation to the gravitational wave signal. So this is the peak frequency for the case of QCD axion dark matter. And the gravitational wave signal at the peak. And so this clearly shows that for the case where you require the correct relic abundance, you're really outside of the observable range of ET or other planned experiments. So that's a clear prediction. Okay, so just to summarize, this was a signal coming from inflationary gravitational waves, how they are enhanced by the dynamics of. You can do the same with other primordial sources like cosmic strings signals. So gravitational waves from cosmic strings, you can see how they are enhanced by a kination era. And this is the result here. I'm showing some examples of spectra. So in black, this is the standard prediction from standard cosmology, and how a very short kination era of a few E-folds would distort the spectrum and lead to this kind of peak structures. And we have studied how you can probe these types of signals in a very general way. And here we are showing, let's say we are assuming there exist ultra high frequency gravitational wave detectors, which are sensitive, for instance, at 10 kilohertz for some sensitivity, which I imagine was like 10 to the minus 10 for omega h squared. And this is, yeah, typically the kind of energy scale for kination you would be able to probe. Okay, I'm not exactly sure how much I do with time, but I'm almost done. So we did this for local strings, and you can play the same game for global cosmic strings. So you have different relations because now the peak frequency is kind of shifted. So these are the typical spectra you would get again. And now something very interesting is that you combine the signal from inflation and from strings, because in principle you have both, right? So, well, at least you have inflation, but as soon as you consider cosmic string, you also should add up the signal from inflation, and then you will these two peak structures. So then you could see one peak at LISA and the rest at high frequencies. Okay, and to finish, this is a signal from now global cosmic strings, where you have also these very characteristic peak signals here. Good. So let me then conclude already. Kination is something very interesting that has been discussed in the literature, but so far in the literature, it was only discussed in the context of really kination following inflation. And what we have, and in this case, it's pretty constrained. What we have discussed instead is an intermediate stage of kination inside the radiation era. And this turns out to be naturally happening in a number of Axion models. So the idea is that the energy density of the universe is dominated by kinetic energy of a scalar field, and in particular of the Petchy-Quinn field. And this will enhance primordial long-lasting sources of gravitational waves. I didn't have any time to discuss really the dynamics of the Petchy-Quinn field. It's very rich, and we have been studying this in detail, and we are about to release the results of these studies. We are now polishing, so it will appear very soon. There are many non-trivial aspects like thermal effects that you have to take into account. Okay, so mainly the gravitational wave amplitude, something important to keep in mind is that it's related to the duration of kination. So the longer kination, the higher the gravitational wave amplitude. And the peak frequency depends on the duration of kination and on the kination energy scale. And so what I have discussed applies to any axion-like particles, and in particular to QCD axion. But for the QCD axion, if you ask that it's dark matter, what you find that the signal, so this peak, will show up only at ultra high frequencies. So I'm done. Thank you.
Thank you, Geraldine. So we are actually quite a bit into the nominal coffee break. So maybe if it's okay with the organizers, what I'll suggest is we can view this as a coffee break now. So somebody wants to go and grab a cup of coffee, they can, and just view this as an informal chat. After Geraldine and Richard's talks, we'll take questions for Geraldine. And if anybody has any questions for Richard too, please raise your hand. So we'll go in order. So Juan, please go ahead.
Thank you. Nice talk, Geraldine. I enjoyed it very much. Now, it's true that it's crucial, the duration of kination, but also it's very important, the duration of matter era before you have kination. So we know that in the matter era, any fluctuations, doesn't have to be very large, it would collapse to form black holes. So if this matter era lasts for long enough, you would have so many black holes that they would already contribute to most of the energy needed for the expansion of the universe. So there would not even be a kination era. So you would have a matter era immediately after, and you change completely the usual evolution of the universe. So I would be worried about what happens before kination. So I would worry about the contribution of black holes to the scenario.
So this is crucial. So the duration of the matter era, the matter era only lasts also a few EFOLs. And so once you take given Axion models, you can compute this completely. So you follow the evolution of the energy density of your scalar field, and you can really predict exactly the duration of the matter era and the kination era. And yeah, I don't know how long it has to be for production of primordial black holes, but in our case, I think the matter era is, I don't know, 5-6 EFOLs.
That's enough to overproduce black holes and dominate the whole density of the universe, but that's something which can be computed. You see, you don't have any pressure, so nothing prevents collapse. Any fluctuation, even just continuing from the CMB fluctuations, 10 to the minus 5 at the scale, you're talking about 100 to 10 to the 5 GeV, if that's correct. Those scales, you would collapse to form black holes. Yeah, with masses about planetary mass. And enough of them, rather than being suppressed, like what you have at QSD when it's very tiny, so the number of EFOLs of QSD, and also you don't have zero pressure. We know it's not a first order, it's a crossover. Prevents overproduction of black holes. So it's a very exponentially sensitive process. So you could easily overproduce. Many domains would collapse to form black holes. But I'm happy to discuss this later.
Yeah, sure.
So go ahead, Fernando.
Other questions?
Yes. No, I think very nice talk, Geraldine. Nice to see you again. Yes. No, I think touching on the point that Juan mentioned. I think I don't know if I got the picture right, because you have inflation, then some radiation, and then the matter domination may be the field that is oscillating. That's around this minimum. That is the partner of the action. Is that correct? Well, in string theory, this is the standard thing that happens, and you don't collapse to black holes. You just oscillate depending on the field has to couple gravitationally or so. And that dominates the energy density for a while, and then you may have this this effect. Of course, the mathematics, the calculation will be slightly different because the action appears in a slightly different way in string theory. But I think this looks very, very generic. It also reminded me of this spintessence discussions in the past. But the spintessence, I think for that theta dot was a constant, was it?
Yeah, so here in this model, theta dot is given by actually the mass of the radial mode of the Pechiquin field.
Right. But just when you solve the equations, because the nice thing is about
so at least in this first class of models, you see the theta dot is really given by this. So it's all predicted, and once you can show the predictions as a function of the mass of the radial mode of the Pechiquin field. Mm-hmm. In the case of the second class of models where you don't need to invoke at all the dynamics of the radial mode, it will actually now depends on the mass of the axion at the very high energies. Mm-hmm. But sorry, concerning the previous comment that Juan made, I mean, about the matter era, I mean, just forget about kination. There are many models which predict a matter era, right? Inside the radiation era, you could have a period when the energy density of the universe is dominated by some heavy particle, heavy massive particle, which eventually decay. So what the comment you make is very general. It's not just about this scenario with kination. It
depends very much on the duration of that period.
Any matter era inside radiation, right?
Yes, I think so, yes. Anyway, well, thank you.
So I mean, I do encourage anybody with questions to just unmute and ask. So please, Eugene, go ahead.
Hi, Geraldine. Nice seeing you again. Really nice talk. So I have a question about, maybe it's related to what Fernando was asking, but I zoned out a little bit. I didn't finish understanding the question. But so people have looked at this spinning scalar field in the Pechiquin potential as a way to try to get like quintessence field, right? And you know, like people like spintessence. And people quickly stop because they realize that they actually become matter dominated very quickly. because the radial mode gets dominated. So here you seem to have like an initial kick that prevents that from happening. Well, what would be the so I guess my question is twofold. One is that how much of the kick do you need, like just kind of rough value, and two is that at the end of this period, wouldn't the radial mode starts to dominate again, because the energy of this field has to go somewhere unless you friction them away. Then wouldn't you expect like a matter dominated phase at the end instead?
Yeah, so that's absolutely the crucial part, which I have not discussed here in this talk, but that's probably the crucial part about the damping of the energy density of the radial mode. So this question is for this first class. No? So indeed, you give a kick here because of the dynamics of the radial mode. But then you have to damp the energy in this radial mode, and this will happen through thermal effects. So this is the tricky part that we've been studying. And so you consider the interactions with particles in the plasma, interactions of this radial mode with the particle in the plasma, and we determine at which temperature this damping happens. So this sets some constraints on the parameter space. So we studied carefully the parameter space where you can indeed have these damping effects to make sure that energy density is dominated by this by the kinetic energy of the axion and not of the radial mode, which would make only a matter era. I fully agree with this. So in fact, it's constraining, but there is still a region of parameter space which is left. But that's one of the really crucial aspects here that requires, I think, some more careful analysis of the thermal effect, and it's not so trivial. But you can assume some typical rate for thermal interactions. So you can add a Yukawa coupling. So this can happen from fermion interactions with fermions, but also gauge bosons. So there are different types of thermal effects you can consider. But let me stress again that this problem only arises in this first class. And when you consider the second class of model, you don't have to worry about this.
Thanks a lot.
So just to summarize for everyone, yes, the key aspect when the kick is given by the dynamics of the radial mode, you have to kill the energy density in this radial mode. And so you have to very carefully look at the thermal damping effects. Yes.
Thank you.
So just to emphasize, everybody, we are starting at noon on schedule. This is sort of like we should think of this as a coffee break. So please, don't feel obliged to stick around for the discussion. It's just, and please don't even stick up your hand. Just ask a question. It's a very informal part of the proceedings.
Okay, can I go ahead then?
Yeah, of course.
Okay. Hi, Geraldine. Very nice talk and very nice idea, actually.
Hello.
I really like it, honestly. It's the first time I'm hearing maybe to make out of Keynesian domination, some realistic observable signal, no? So it's very nice. Actually, I was going to make a comment that could be hopefully interesting for your own research, no? Which is, you've been concerned so far here showing the ability to measure this with direct detection, right? Showing the prospects of different observatories, no? But I think you could put immediately constraints from BBN and delta NF. Maybe you've done it already, no? But I suspect the parameter space constraints should be super big, no? Based just on that, right? Delta NF, for instance.
Well, so we did this. Actually, you had this in your paper. You started to do this, and this is summarized here, but this is very constraining for Keynesian era right after inflation. Now, for short Keynesian era, the constraints from BBN are small, and they are shown here. So this is as a function, the prospects as a function of Keynesian energy density.
I was more thinking in your Axion dynamics, no? Because you must have some parameters that control the onset of Keynesian, and so on. So you should be able to put constraints into the angular velocity you start with, in the mass combination of these parameters, right?
Yeah, you will see all these plots in a few days. Yes, okay. So I didn't show them today, but you can in fact now show for a given Axion model the constraints in the plane depending on FA or I mean the parameter space of your Axion models, right? But what I want to stress is that this kination dynamics does not depend on the Axion mass, first of all. It's really controlled by the initial velocity. So there is essentially almost the Axion mass does not play a role. It plays a role as soon as you require your Axion to be dark matter, and this is But otherwise, the kination signal has nothing to do with the Axion mass because it's entirely controlled by initial velocity. In fact, yes.
Yeah. Okay. Very nice. Thanks.
But there are, I mean, the constraints. We can discuss later. But the constraints from NF at the end are not. They are constraining, but they are not so relevant. They are not so relevant. A large parameter space open.
Okay. Okay. Good to know. Good to know. Better. Thanks.
Can I ask another, maybe probably a very stupid questions about kination, Geraldine? I think maybe it's slightly related to what Juan was asking just now. So kination do boost gravitational waves by basically diluting everything else, but in principle, it also boosts everything else that it doesn't dilute as a to the -6, right? So if you have a tiny component of matter before kination, it also boosts that. And in fact, any small perturbation that is not kination will get boosted because you're just comparing dilution rates to get this great gravitational wave boost. So would that give you additional constraints about how much kination that you can have? Like for example, what Juan said, that, if we have some matter dominated and then some small perturbation, then you make some black holes, and wouldn't that small matter dominated energy be boosted by kination, or I'm just not thinking this right?
I'm not sure. So frankly, I have not thought about the primordial black hole constraints in this scenario. So that's something we should think
maybe
about.
not even primordial black hole constraint, but any component of energy that is not kination, right? In the kination era would, in a sense, get boosted because the dominant energy, which is kination, is diluting. So everything else is want to take over its place, if you like.
May I comment? I think it's a very pertinent comment here that you make, Eugene. So the thing that will happen is that it would backreact on the metric, and you will have also second order gravitational waves from these. So you could have an enhancement of the gravitational field, a gravitational wave background from this enhancement, relative enhancement of the matter fluctuations, which backreact on metric and produce gravitational wave spectrum. Just like we know from inflation, if you are thinking of collapsing to form black holes and there's somehow an enhancement in the power spectrum, these will be felt when those scales enter the horizon as to second order, as a gravitational wave background. I think this is a very interesting second order effect, which here might be interesting to explore. I think it's a great idea. I haven't thought of that. It's worth looking into.
At some point, I don't remember the conclusion, but we looked at the simplest effect. But there would be other induced gravitational wave signals. I don't know if you remember the answer to this question, but at some point we discussed about it. But that would be less trivial to investigate. That's a different study.
So I suppose I would have had a question for Richard, but he's not here. So maybe this is for everybody present who may know better. The gravitational wave spectrum from Hawking evaporation of lighter PBHs in the early universe, is this the gravitational radiation produced from the produced particles from Hawking evaporation? Is this like a secondary produced gravitational wave source, or is it really direct production of gravitational waves from Hawking radiation itself? How am I supposed to think about it?
I think there's both.
Okay. So
if you heat above the temperature of the plasma, then you're injecting energy into the plasma, and this produces also a gravitational wave source.
I see. Okay. So is it very naive of me to think that if let's say there's some profile you had for some PBH abundance of you know, light PBHs, and you get some bound, I don't know, you get some prediction, you know, omega produced at the peak is about 10 to minus 9. This, I presume, is assuming a standard model field content. But if you had, like, you know, let's say, I mean, is it very naive to think that, like, you know, let's say you had some hidden sectors that only couple gravitationally, that this could also put a crude bound on the number of hidden species? So I can't have more than 10 to 9 hidden species if you're getting 10 to 9 from the standard model, for instance. Is that too naive? Because then you'd be over omega GW1.
Sorry, can we postpone this discussion to maybe the discussion session, because we don't want to restart